Okay, welcome back. And today we are going to start linear functions and applications. And so this is going to cover section 1.2. Hopefully this will go pretty quick. I'm going to try to keep these videos to be half an hour to 45 minutes. But we'll see how that goes depending on how long-winded I am and what we have to go through. Okay, so here's the first thing. So function, what is a function? So a couple of things we have to understand. A function is a rule in algebra. Okay, so when we have a function, it is a relationship between two variables. Not all relationships can be defined as a function. So the idea of a function is that for every x value that we put into the function, we are only going to get one y value. Okay, so for every x value, there's exactly one unique y value. Okay, so now instead of x and y, we use function notation. And so instead of y, since it's a function, we no longer use y. We say that g, and we usually use lowercase letters for functions, but g of negative x, okay, or g of x is commonly the way that we speak. So this is a function, in terms of x, where x is the independent variable, and whatever the output is or the y value is the dependent variable. So again, same thing that you've probably seen before in algebra. So x is the independent variable, and then y is the dependent variable. But in this case, instead of y, we're going to use f of x or g of x in this case, where this is a function of x. And so also we can look at this as this is the input versus the output. Okay, so whatever we put into the function, this is what we get out of the function. Okay, so for example, using this function, whatever we stick into here, this is what we get. Okay, so this means g of negative x gives us this. Okay, so wherever there's an x, we're going to stick in a negative x. Okay, I wonder if this is supposed to be x, but we'll find out in a minute. But this is the rule. Okay, so we want to find what is g of negative 5. So we're going to stick in, wherever there's an x, we're going to stick in a negative 5. Okay, so we're going to substitute in negative 5 for x. So wherever there's an x, we're going to stick in negative 5. So g of negative 5 is negative 4. So this should be x, not negative x. That's a typo. So disregard this negative sign. So it's g of x, not negative x. And so if we stick in negative 5, that means we're going to stick in negative 5 here for x. And so notice the parentheses, okay, because the whole negative x, or excuse me, negative 5 is what we're substituting in for x. So now negative 4 times negative 5 gives us a positive 20. And so plus 5 gives us 25. So when we stick in negative 5 into our function, we get 25. Okay, so here is the definition. So a linear function is a relationship of f, right? So it's a linear relationship f defined by this. Okay, so a linear function is like a linear equation. So we just start talking about linear equations, but now we're going to look at them as functions. Okay, so we're going to, instead of y, we're going to say f of x is equal to mx plus b. And so this is what we call a linear function, where m and b are real numbers. Okay, so instead of calling these linear equations, we're going to look at them as a linear function. So let's look at supply and demand. So supply and demand are very commonly used in economics. It's one of the basic principles of economics, supply and demand. And so we're going to look at supply curves and demand curves. Okay, so in this example, it says, suppose that Greg Tobin, manager of a giant supermarket chain, has studied the supply and demand for watermelons. He has noticed that the demand increases as price decreases. Okay? He has determined that the quantity in thousands demanded weekly, Q, so the Q is the number of watermelons that are demanded, and the price in dollars per watermelon P are related by a linear function. So let's say this is what we're going to call the demand function. So demand is how many widgets um, are being demanded. So it's a function of Q, right? So price, which is going to be D of Q, which is going to be the demand function, is represented by this linear function. Okay, this is what we're going to call the demand function. Okay, so now one thing to keep in mind, in economics, price is the independent variable, really. Even though right now we're using it as the dependent variable, it really, in economics, it is the independent variable because the demand is affected by price, not the other way around. So again, just a distinction that you want to keep in your mind when it comes to economics is that price is actually the independent variable. And if you think about it in real world, it is the independent variable. So as price increases or decreases, demand for that product is going to increase or decrease, or the supply is going to increase or decrease based on price. Okay, not the other way around. Even though this is typically in economics the way they do it, but realizing price here is the independent variable. Okay. Okay. So anyway, so A says find the quantity of watermelons demanded at a price of $3.30 per watermelon. So here's the price, and we want to find, okay, what's the demand at that price? Okay, so what do we know? Well, we know that price is equal to $3.30, and we know that price is dependent is equal to this demand function, which is based on the number of widgets. Okay, so now what we can do is we can substitute $3.30 for P, and then what we could do is we could solve for the quantity Q. So that's what we do. And so now all we have to do is solve by subtracting 9 from both sides, and that gives us a negative $5.70. And then now we've got this negative 0.75 that we're going to divide both sides by, and then we get a 7.6 for Q. Okay, so now it says, thus, what is our conclusion? Our conclusion is that if the price of watermelons is $3.30, then the quantity demanded in thousands, remember in thousands, is 7,600 watermelons. So if we set the price of watermelons at $3.30, we can expect that the consumers are going to want to buy 7,600 watermelons. And so that's what we should provide, right? So now Greg also noticed that the quantity of watermelons supplied decreased as the price decreased. So price P and supply Q, right, the number of watermelons supplied, are related by another linear function. And so let's say this is the linear function. So price is equal to the supply function, which is, in this case, 0.75 times Q. Now, we want to find what is the quantity of watermelon supplied at a price of $3.30. Okay, so now, based on the supply function, how many watermelons are supplied by the company if the price is $3.30? Well, again, we're going to substitute in for $3.30 here, and we're going to set them equal, and we're going to solve for Q, which is the quantity. But then in this case, it's the supply quantity. So what's this? What does this mean? So at $3.30, what does that mean? It means the supply is going to be 4,400 watermelons. That means that at a price of $3.30, the quantity that the company will supply based on that is going to be 4,400 watermelons. Well, what's going on here? Well, based on the demand curve, at $3.30, people are going to want watermelons. Okay? And the supply curve says, well, we should only be supplying 4,400 watermelons. So what's going on here? So now what that means, if there's something called a shortage and a surplus. And so in economics, if the demand is higher than the supply at a particular price, then what we're going to have is you're going to have a shortage, in this case, a shortage of watermelons. Okay, and so what is that going to do for the price? Well, it's going to affect price. Price is going to start to increase. Okay, and what if it's the other way around? What if you supplied 7,600 watermelons, but there's only a demand for 4,400 watermelons? Well, in that case, you have a surplus. You have too many watermelons that are being sold or being supplied to the market. So that what's going to happen with that? Well, in that case, the price is going to be driven down because there's too many watermelons, and to get rid of them, you're going to have to mark down the price. Okay, and this is one of the basic fundamental principles of economics. Okay, supply and demand. So now there's something called an equilibrium quantity. Okay, or an equilibrium price. So what does that mean? It's where the demand curve, where the demand for watermelons and the supply for watermelons are equal. And we want to find out, hey, what is that price and what is that quantity? What is the equilibrium quantity and the equilibrium price? In other words, what price would we need to sell these at so that the demand and the supply are both the same? Okay, so how do you find that? Well, set these equal to each other. So the equilibrium quantity is found when the prices from both supply and demand are the same. So what we're going to do is we're going to set both of these functions equal to each other and solve for Q, and that's going to be the equilibrium quantity. Okay, so let's do that first. Well, if you do that, what do we get? Well, again, we're going to solve for Q. So we're going to add 0.85 to both sides, and we get 1.25. And then what we're going to do is then divide by 1.25, and we get Q is equal to 8. So what is that? 8,000, right? So the equilibrium quantity is 8,000. So the question is what price do we need to set it at in order to get there? And that's going to be the equilibrium price. And so what you have to do is just take the 8 and plug it into either one of these two equations, and you will get your equilibrium price. So the equilibrium quantity is 8,000. So what's the equilibrium price? Well, looks like the equilibrium price is going to be $3.20. So if you just mark it down by 10 cents, you will hit the equilibrium quantity, which means you're going to save, or you're going to sell 8,000 watermelons a week. Okay, so here's what the curve looks like. Okay, so here's what we have. So notice that what's this? The supply curve is increasing, and the demand curve is decreasing. So notice that price. Now here's another thing to keep in mind. They have price as on the y-axis, and that is by construction. Again, that goes way back in the 1960s by a famous economist who I can't remember off the top of my head, but he's the one that started putting price on the y-axis. It should actually be, if you think about mathematically, because it's the independent variable, it should be on the x-axis. But nonetheless, that's the construction. So notice that what happens as price increases. When price increases, supply is increasing. When supply increases, demand is decreasing. So we want to find that sweet spot where price will give us the equilibrium, where demand and supply will be the same. Okay? So now, and so how do you do this on your calculator? You can do this on your calculator by using your y equals key. And then you can plug in your demand curve or your demand function and your supply function on y1 and y2, and then plot it on your calculator. Okay, you may have to adjust the window, but you can get this on your calculator easily. Again, if you have any questions about using the calculator, ask me in class. I'll be more happy to show you how to do this. Okay, once you do it a few times, it's very easy. Okay, so here's a couple of things. So some of the things that I talked about earlier. So what happens in different prices? So let's talk about different prices. What if our price is up here? Let's say we set up our price in this area here. Okay, so let's do this. So what if we set our price right in this area? Okay, well that means where are we going to be at? Well, we're going to be up here, which means our price, what? Is going to be in the surplus area, right? Which means that for this price, the supply is going to be where? It's going to be up here. Okay, so if we are here, okay, so if we have our price up here, okay, what's going to happen? Well, quantity, what's the quantity going to be like? So quantity is going to be up here, which means we're going to have a surplus. Okay, so notice that in this here, we have three different places. Okay, if we have our supply curve, right? So let's say supply curve here, and we set our prices, right? Again, supply goes up as price goes up, so it's increasing. So at this price here, this is where we're at. Okay, but the demand is down here, which means we're going to end up having a surplus of watermelons, let's say, or widgets. But then because of the demand, we're going to have to drop our price to sell them. So it's not good to have a surplus of things for a company and the demand for them is going to go lower, because the more things that are in the market, the demand tends to go down. So as price goes up, demand usually goes down because people are not going to, they're only going to pay so much for something, right? But what if your price is over here? Well, again, as price decreases, supply decreases. Okay, but as price decreases, demand tends to be higher. And this is where you get a shortage. Okay, and again, when there's a shortage of things and the demand's high for them, price tends to go up. Okay, and usually the equilibrium spot is where it tends to be stable, where this is about where the market and the company are in agreement, if you will. So equilibrium, what is equilibrium? It says when supply and demand are equal, the economy is said to be at equilibrium. The equilibrium price of the commodity is the price found at the point where the supply and demand graphs for that commodity intersect. The equilibrium quantity is the quantity demanded and supplied at that same point. Now, let's talk about linear cost function. So now that we're talking about economics, the next thing to talk about is, okay, when you're producing widgets, you have cost, right? There's a cost to produce or to make something, right? Everything has a cost, okay? In a cost function of the form, again, we're going to talk about linear cost, a linear function. Cost is of this form, where you have a cost per widget, but then you have this fixed cost, right? So it is actually made up of two quote unquote costs. You have the fixed cost and you have the per widget cost, if you will, okay? So the M represents the marginal cost, the amount it costs to make one more widget. Okay, and since we're talking about linear um, functions, this is very easy to understand um, when it comes to marginal cost, because in general, that's the way some economists look at it. And some textbooks is it's the cost to produce one more widget. And since we're talking about linear functions, it's always the same. So the marginal cost will always be the same. Okay. So this is M represents marginal cost, and B is what we call the fixed cost. So conversely, if the fixed cost of producing an item is B and the marginal cost is M, then the linear cost has to be this for producing X widgets. Okay. So this is the definition of what a linear cost function is. So let's look at an example of this. So the marginal cost, okay, they're telling us the marginal cost to make X batches of a prescription medication, whatever it is, Zoloft, pick your poison, okay? Let's say it's $15 per batch, okay? We don't know how much a batch is, but let's just say it's $15 per batch. While the cost to produce 80 batches is $1,930. Okay, so let's see that. The marginal cost is $15 per batch, while the cost to produce 80 batches is $1,930. So it says find the cost function C of x given that it is linear. Okay, so let's see this is a linear function. So we know it has to be of the form of C of x is equal to mx plus b. Well, we know what m is, right? It's 15. So we know it's $15 per batch. We also know what x is for a particular amount, right? We have 80. And we also know what the total cost is, right? It doesn't say fixed cost, it doesn't say marginal cost, but it says cost. So we know this is the total cost. So this has to also include our fixed cost. Because if you take 80 times 15, right, so that would be our cost to find 80 batches, the cost of making 80 batches of prescription at $15 per batch is how much? Well, 80 times 15 is what? Well, 15 times 8, right, is 80 plus 40. So 80 plus 40 is 120. So that's what? $1,200, right? So 80 times $15 is $1,200. Well, that doesn't reach the 1930. Well, guess what? That means the rest of it has to be fixed cost. So if we take that 1,200 and subtract that from the 1930, what do we get? We get $730. And guess what? That is going to be our fixed cost. That's going to be the B. And that's going to give us our answer. Okay. Now, look at what we did. So that was basically walking through it. Okay, kind of like it out loud, talking about it. So now let's put it together. So the marginal cost is $15 per batch, which gives us our M. So we know using x equal to 80. Okay. Now again, they use the point slope form. You don't need the point slope form to do this. You can use y equals mx plus b and just plug in 80 for x and then solve for your b. But the same thing. They get the same thing, 730. Okay. So you distribute the 15x plus minus 1200. There's our 1200 that we got. Okay. And then you're going to add the 1930 to both sides. And what is it going to mean? It's going to mean you're going to subtract the 1200 from the 1930 and you get the 730, which is what we got before. So this is our cost function per widget for widgets. In this case, prescriptions. Okay, now look at this one. Here, a company has a fixed cost. Now they're giving you the fixed cost of $7,145. The total cost to produce 100 widgets is $7,965. So now you've got the fixed cost, and now you've got the total cost to produce 100 widgets. Okay, now widget is a term that's often used by economists to just refer to an abstract production. It doesn't matter what it is. It could be pickles, it could be bananas, it could be fidget spinners, if you're into that. It could be Xbox consoles, whatever it is. So it's just an abstract unit of production. Okay. So now it says find the cost function c of x. Given, again, we're assuming that it's linear. So that means if we know the cost function, that we got b, right? So what do we do? Well, we know that this is part of this total cost. So what we can do is we can subtract this amount from the total, and whatever's left over has to be part of the marginal cost, right? Okay, so if we subtract this from here, what do we have left over? We'll have 820. Okay, so we'll have $820 left over. And now that's $820 that was made off of making the 100 widgets. So if we then divide by 100 widgets, we'll get the price per widget, cost per widget. So if we take the leftover 820, divide by the 100, we get what? $8.20. Okay, and then that's going to be our M, our slope, the marginal cost. Okay, so here's the solution. So again, B is the 7145, because we know that the cost function has to have this form since it is linear. And so we need to find the marginal cost M. So again, we can subtract, right? The marginal cost is going to use the value of B along with the x100. So we know that C of x equals 7965. Okay, so if we use our mx plus b and we plug in our values, right? Well, guess what? We're going to subtract off the 7145, and then we're going to divide by 100 because we're going to solve for m. Isn't that what we just did? So we get 820 divided by 100m, right? Or equal to 100m, so we divide by 100. And then when we divide by 100, we get 8.2. So that means the cost function is c of x equal to 8.2 times x plus 7145, and the marginal cost is $8.20 per widget. So it means that, hey, to manufacture or to produce one more widget would cost an additional $8.20. Okay, so now let's talk about break-even analysis. So that's often in economics and business. You want to say, okay, what's my break-even point? Where am I going to be? Where am I going to break even as far as cost and revenue? Okay, so let's talk about revenue. Okay, so it says let P be the price per unit and let X be the number of units sold. So that's the demand, right? So the revenue in this case is the amount of money that's coming in based on the widgets sold. Okay, so revenue is always price times the number of widgets sold. That's going to be how much money is coming in. That's revenue. It's always going to be price times the number of widgets. Profit is the difference between your revenue and your cost. And it's always revenue function minus your cost function. Because if your cost function is bigger, if it costs more to produce than what you're bringing in, then your profit is going to be negative, which makes sense. You're in the red. Okay. So the profit is going to be your revenue function minus your cost function. Okay. Now, what if we want the break-even point? Well, the break-even point is where your revenue your revenue is the same as your cost. In other words, your profit is 0. So in other words, the difference between these two is 0, or they're equal to each other. So the break-even point is where your revenue function is equal to your cost function. Okay, so now the break-even quantity can be also found by setting the profit function equal to 0. So again, remember, if there's no difference, if these are the same, if you're at a break-even point, then your profit is 0. So you can go ahead and put 0 here and solve for this, and you get the same thing. Okay, so the break-even point is the corresponding ordered pair and indicates the point of 0 loss or 0 profit. Okay, so if we look at two functions, right? So we look at our cost function and we look at our profit function. Okay, now remember, or excuse me, not profit function, revenue function. So here are the two functions. So where they intersect, so again, keep this in your mind when you're graphing these, the intersection point is the break-even point. That's where your cost function and your revenue function are the same. Now, what if you're down here? Let's say the amount of money, right? So this is here, and this is units of feed for this graph. And so let's say you've got this, the amount of money that's brought in, right? And so here, what if you're in this area here? Okay. What if your price is in this area? Okay. Well, if your price is here, then what you're going to be is you're going to be operating at a loss. Okay, if you're only selling this many. Okay, so if anything in here, if you're in here, you're going to be operating at a loss. If you're up here, then you're operating at a profit. Okay, because if you notice here, your revenue, if you look at the amount of units you're selling, okay, if you're selling this many 3,500, whatever this may, 35, let's say, then you're going to be in this area here, and you're going to be operating at a profit as long as you're in this area here. So again, it's based on what this is and what this is. Okay. So this is what we call a break-even analysis, a cost analysis. Okay. So this tells us, hey, where we have to be to have a profit, where we have to be if we're going to have a loss, or if we just need to break even. Okay. So the break-even point here is at 25 and approximately 600 right here, 25,600. Okay, so now in this here, we want to derive an equation relating Fahrenheit and Celsius. Okay, so there is a linear relationship between Fahrenheit and Celsius, degrees Fahrenheit and degrees Celsius. So, and it's given by this graph. So we're going to use this graph, and we're going to use the freezing points and the boiling points of water. Okay, so we know that the freezing point of water is 0 degrees Celsius, which is the same as 32 degrees Fahrenheit. And the boiling point of water is 100 degrees Celsius and 212 degrees Fahrenheit. Okay, so notice that this is Celsius and Fahrenheit. So the first thing we need to do is what? Well, we've got 2 points, and we need to figure out the linear relationship and derive the function that relates Fahrenheit and Celsius. Well, we need to find the slope of this thing, right? So we've got 2 points, right? Let's find the slope. So we're going to use the slope formula, okay? So we're going to take 212 minus 32 divided by 100 minus 30. So it's going to be y2 minus y1 divided by x2 minus x1. And so when we do that, we get this. So our slope turns out to be 9 over 5. So again, you always want to reduce this into the simplest fraction. Okay, so now it's 9/5. Okay, now notice that this is what? Fahrenheit over Celsius. Okay, so now the F-intercept is what? Well, they give us the F-intercept because it's F here, so degrees Fahrenheit. So the F-intercept, so when Celsius is 0, F is 32. So the F-intercept is 32. And guess what? This is your slope. This is the F-intercept. And C is your X variable. So it's going to be degrees Fahrenheit is equal to 9/5 degrees Celsius plus 32. And it makes sense because if we have freezing point of water, then in degrees Celsius, it's 0. And then 9/5 times 0 is 0. And all we're left is 32. And so the freezing point of water in degrees Fahrenheit is 32, which is what we started with. If we say 100, if we put 100 here, we're going to get 212. Okay? And so this is the conversion formula for going from degrees Fahrenheit to degrees Celsius, or by you could also solve for C and you get a similar formula, okay, which would be F minus 32 times 5/9, okay. Okay, and that ends our lesson for today. And again, if you have any questions, make sure you read the textbook. Make sure you bring your questions to class, and anything you have, please write it down. Write your questions down, bring them to class. If there was something you didn't understand, something from the textbook, maybe do some of the other examples, do some of the try it yourselves or the exercises at the end of the section. And if you get stuck in anything, bring those to class and ask about them, because that's where you're going to practice. Okay, talk to you later and have a great day.